Hey everyone, how are we doing? Good to see you here. What questions do we have today? I know we didn't have office hours yesterday, but we have them today. I bet some chapter 13. What chapter are we going to work on? I'm so not used to glasses. Oh. I think they got smudges right there. Can't see. Can't see on my glasses. No. Look at that. This will be better. So nice. There we go. There we go. Much better. Much better. For the moment. For the moment. Let's see. What questions should we do? It's your call. It's your office hours. What do people want to do? Good to see you here, Savannah. I think Mubot, we just woke him up. Throw out some points right here. What should we do? We got a full office hours. Grab some lunch here in a little bit. What questions? The most missed test questions. So, generally speaking, and then which part's chapter 13? Let us know. So, a lot of times with the test, the notation is usually where people fall flat. It's usually like, and so you have to write every bit of notation down. I think that's the part that I always say do, and I hope everyone does. But the notation is usually where the problems are at. So you have to be able to see the notation, understand it, and then be able to decipher a problem with it. So let's start here. Do chapter stats 1, chapter 13 notation. Okay, let's check out some chapter 13 notation. Okay. So when we do chapter 13, there's a whole lot of notation you have to know. And the notation starts with things like P hat, and then I guess we have Q, hat, we have N, we have Y bar, we have mu, we have mu P hat, got so many of them. Go. And then we have sigma, mu y bar, and SD y bar, and then we have mu p hat. SD. Are you wondering about any of these? Any of these in notation? Any single one of these? Do you know every single one of these in notation right here? I would know all of them. Someone has to be saying, no, I know none. Savannah, you know all of them? Awesome. So if I were to say, so be careful here, right? I'm going to try to trick you. Let's see if we can do it. You ready? If I were to say, UT students have a high school GPA of 3.6, which of these would it be? Oh, you need help? Okay, good practice. We'll do some practice here. UT students have a high school GPA of 3.6. Which of that would these be? Just a practice. Don't worry about getting it wrong. Throw 100 points for every answer. UT students have a high school GPA of 3.6. I think yeah, that's mu, right? Great job. That's the right answer. So mu is the true mean. There's no sample size associated with that. It's just the truth for all. Wouldn't be proportions, though, because think about mean. If you ask someone what their GPA is, how would they answer you? So if you ask someone what their GPA is, how would they answer you? So when you ask someone, what's your GPA, that's a what kind of question. So I've actually subdivided this right here to where the top is proportions. Now, N is for both. So we could put N down here also. I could disappear for the moment. And then the bottom is quantitative. So the top is all dealing with proportions and the bottom is dealing with quantitative. So if you say UT students have a GPA of 3.4 for their high school GPA, that's mu. But if you say I talked to 100 students, well, the 100 students you talked to would be the sample size. And I guess we could put here population size. So I talked to 100 students, which is the sample size, and the GPA of the 100 students was 3.7. What is the 3.7 in notation? A lot of practice right here. So this is a good, see if you know what it is. The 3.7 in notation there would be what? I talked to 100 students and their GPA was 3.7. I talked to 100 students and their GPA was 3.7. That's not notation for it. I'm just saying what those things are. That's mu and sigma. Like it's not mu sub mu, sigma sub sigma. I'm just putting what they are next to it. So if you're wondering, that's a sigma and that's a mu. So if you talk to 100 students and they had a GPA of 3.7, the GPA of 3.7 from the sample of 100 would be the sample mean. So the sample mean is y bar. That's the mean, because y is an observation, like a singular GPA. Great job right there, Jesse. A singular GPA from one student would actually be an observation y. And then the GPA for the average of students, 3.7, yep, is the sample mean, correct. 3.7 is the sample mean. And then we get into, well, what the heck is this thing? What is mu y bar? So this is a full notation for the expected sample mean. So think about this. In our example right here, we said that students have a high school GPA of 3.6. If you were to go out and take a sample, what would you expect the sample mean to be? If you, and good to see you here, Kelsey, if you were to go out and take a sample, what would you expect the sample mean to be? If you took a sample, what would you expect the sample mean to be? Now, not what is the sample mean, what is the expected sample mean? And that's how that is read right here. It's read expected sample mean, 3.6. Exactly. That's because if they have a high school GPA of 3.6, then we'd expect to see a high school GPA of 3.6. And that's what we get right here with mu y bar equals mu. Now, that might seem confusing, but it's saying, think about this. The average student is 5'8". I go out and talk to 10 students. What would I expect the mean height of 10 students to be? So if the average student is 68 inches tall, then what would I expect the average of 10 students' heights to be? Not saying what it is, but what would I expect it to be? Like if I talk to 10 students, I'd expect their average height to be what? 68 inches. So it's the same thing, but you have to understand we're not doing true population mean times sample mean. It's read expected sample mean. So I expect the sample mean to be around the true mean, or that's the most likely thing to see, which is why we put it at the center of the curve when we draw these curves out for the problem. And I think we have one of them drawn right here. So we put the expected sample mean at the center of the curve, because in this problem, this is mu. So mu y bar is equal to mu right there. So this problem told us what the height of students was. It was 70 for this problem. And then we talked about what would be unusual, and we need to find the standard deviation for that. So the standard deviation, which is right here, is the variation around what we expect to see. So we have what we expect at the center, and then we have the standard deviation, which creates the width of it to show the variation in what is possible. And there's different standard deviations depending on if we're doing quantitative or categorical data. So the first thing you have to do for any of these problems, and we'll do a practice problem here in a moment, is you have to identify, is it categorical or is it quantitative? So let's start by doing this, because this leads to the notation, and it leads to the conditions, and it leads to the notation. So think about this. If you're taking data on if students are born in Tennessee, ask yourself that question and answer the question yourself. So as long as you feel okay with putting in the chat, the answer for me is no. So, well, there's my answer. But think about how you're answering that, and then look at your answer and think, did I answer quantitatively or categorically for born in Tennessee? I think a lot of people get confused because you're still doing like an expected or mean sample portion in right there. Jesse did it perfectly. Categorical, right? Are you born in Tennessee? Yes or no? So the proportion of students born in Tennessee is a categorical question. So you have to think, what kind of question am I working with? Where GPA or height, like if you do GPA, I had like a 2.8 in high school or something pretty bad, 75 inches. Both of those are a quantitative answer when you say like, how much is your GPA? How tall are you? Both of those are quantitative in nature. So very important, we look at the question, we think, what kind of data is this leading to? And if we see it's quantitative or categorical, we know the answer of which formulas we're using. So all of this notation is super key right here. We have here, and I'll just mention all of them. What is the notation above the square root? Which one? Let me go back. I think it was on the previous page, right? On the previous page for the standard deviation. Above the square root, that right there, that's a sigma. Is it this right here? Sigma over square root of n. Sigma is true standard deviation. So the sigma is the true standard deviation. Thank you for asking, Savannah. So that's the true standard deviation. So you see how it says right here in this problem shows it off, where it says males males at UT have an average height of 70 inches tall with a standard deviation of 3. And this is stated as truth. It doesn't come from a sample. And I think that's where people usually make mistakes, is down here on the bottom. We are now taking a sample of 100 guys. So that's an N right there. And then this is a sample mean. So that is a sample mean from the 100. So you can't just say the mean. You have to think about, is it the true mean or is it the sample mean? Is it the true standard deviation or is it a sample standard deviation? We usually don't add that into these problems, but sample standard deviation is S. So the notation is so very important for the remainder of the semester, because if you have the notation, you can solve most of these problems. So here's all the notation, and then the formulas are over here also, with the standard deviation of p hat being p times q over n square root, the standard deviation of y bar being sigma over square root of n, and the last conditions right there. What homework questions? I mean, this has just been a quick overview of all the notation you need to know and how to use the formulas, because the same holds true for p hat, or for p right here with mu p hat, where if it's true that 40% of students are from Tennessee, if you took a sample, you would expect to see in the sample 40% of students from Tennessee. That's the most likely thing to see. It's not that you will see that. It's just the most likely sample proportion is 40%. What questions are there? Let me know, because Savannah, are you wondering about some chapter 13 homework or quiz problems? It's your office hours. We do whatever people want. So if you're watching this in the future and your problems didn't get encountered, let us know. Be like, hey, wait a minute. I need help with this problem. Which problems should we do? What should we do? Surely someone's like, wait, I need help with this one. I'm going to fall asleep. No. Which problems should we do? Chime in at any time with any problem you want done. I'm going to open up my Pearson here. Suppose the probability bus driving on time was for the next 5 stops probability. That's is that the canvas content, Savannah, right there? So that's canvas content number 6, right? Canvas content number 6, I think. Yep. Okay. Let's do that. Canvas content number 6. Okay, let's check it out. Okay, so suppose, there we go, got it. Suppose the probability of a bus being on time is 0.59 for the next 5 stops. What is the probability the bus is on time for at least one of the stops? So this is an at least one problem right here, and you have to write out the sentences. That's the number one way to solve this. But let's first write out our probabilities. What are the probabilities, Savannah? So what are the probabilities that we have right here? So we have the probability or the event and the probability. So we have, yep. So we have event, on time, and not on time. So what's the other probability here? So and then the probability of the So what's the other probability here? So this uses the complement rule. What is the other probability? This uses rule 2 also, that we can figure out the probability of all the events. So would be, yep, great job, Savannah. Excellent job. 100 points right there. And so now we have to write out a sentence. And so when you think about this, we have a bus going to 5 stops. And it says, what is the probability the bus is on time for at least one of the stops? So if we use like a thing right here that it missed the stop, and so we'll do not make right here. Now tell me, was this bus on time for at least one of the stops? So you look at my color coding. Was the bus on time for at least one of the stops? Yes, perfect. It was on time for 4 stops. Was it on time for at least one of the stops here? So you'd look at the color coding. Was it on time for at least one of the stops? For this scenario, was it on time for at least one of the stops? What do you think? Well, how would this be described right here? Yep, Jesse's right. Yep. It was on time for all the stops. When is it not on time for at least one of the stops? When is it not on time for at least one of the stops? Like, describe to me the scenario when it's not on time. Exactly, Jesse got it right there. All the misses right here. So in this scenario, it is when it is late to all 5 stops. And it's either late to all 5 stops or on time to at least 1. And why does this equal 1? Why does this thing I wrote out right here equal 1? Because it's either late to all 5 stops or it's on time to at least 1. Why does this mathematically equal up to 1? These two things are what of each other? Because either it's late to all 5 stops or it'll be on time to, well, they do, we can add these up. We can add up the probability of this and the probability of this, and they are complementary. Because think about this. It'll either be late to all the stops or on time to at least 1. Think about this this way. If you buy a lottery ticket, either all 5 will be losers or you'll win on at least 1. Does that make sense? Like, at least one of your tickets will be a winner or all 5 lottery tickets will be losers. So you're just saying everything that could occur right here. So we're going to change the or to a plus because these are complements and thus disjoint. They can't occur at the same time. So how can we figure out the probability of late to all 5 stops? What is the mathematics for late to all 5 stops? How can we figure out the probability of it being late to the first and late to the second and late to the third? How do we figure that out? What would that be mathematically? Late to the first and late to the second and late to the third and late to the fourth and late to the fifth. Yep, Jesse has it right there. And it's just multiplying it together a whole bunch of times. And there we go. And now we algebra it. And we bring it over to the other side. And there it is. And just solving through. Does that make sense, Savannah, right there? That is how we solve it right there. And Jesse's got the answer for it right there. But writing it out, seeing the steps, understanding how to do it right here, basically making a table, understanding how these are complements, being able to write out the sentence, understanding that when we add things, they are disjoint. So it's a good problem to practice and understand the steps But you need to be able to write out the sentence, and I would just suggest drawing it out also, because then you kind of understand what you're seeing. You're like, okay, it's either late to all 5 stops or on time at least once, and then I can add those up because they're disjoint, because they're complements. Um, what if it asks what's the probability that 2 were on time for one of the stops? We wouldn't actually do that. There are ways of doing questions that are pretty complex on the test. Like we do have some tricky questions. That would be a question we wouldn't do. There is one on the test that I've seen before that I don't want to give away, but it's a tougher one where you have to think about what you can do. It's probably one of the toughest ones, I'd say. It's only worth like 2 points. So someone's like, what is it? But we would never do like exactly 2. The way of doing that is you'd have to figure out the permutations of the way that 2 could occur. So you could do that, but that's a more complex problem. That requires combinations of outcomes. But it's not too complex. You set up the ways in which it can occur. And yeah, like what if it was on time exactly to 1 stop? Well, there's 5 ways that that could occur. So you would times the probability by 5s for it being, it would be basically here. If you want to know what's the probability it's on time to exactly 1 stop, then you'd go 0.59 times 0.41 raised to the 4th power. And then this whole thing right here would get times by 5. And this is something we don't usually do, but this is the probability on time to exactly 1 stop. And the reason is because if it's on time to exactly 1 stop, it could be on time to this one or to this one, and that's why we can add them, because there's different combinations of ways it could occur. And we could say it could be on time to this one or this one or this one or this one. So you're actually adding this a bunch of times right here, and each one has the same probability of the 0.4 to the 4th power times 0.59. So that's that one's that one, and then there's more combinations for the other one. It would be, I'm trying to think how many combinations it would be, but there's formulas you can use for it, and then there's calculators also. So I would preferably just use a calculator, like if I was solving these personally myself, I would go over here to the binomial applet and so the binomial applet can easily let you solve these. So we're looking at the probability of it being late or so, and then we can enter in 5 trials, and then you can see the probabilities associated. There's that probability we got right there. If we take 1 minus it, there it is right there, 0.1159 right there. Is typically always, well, it's not p hat though. This is not p hat. It's a good question. This is just a probability right here. So this would not be p hat though. P hat means sample proportion. So this is just a probability. So this is the event and the probability of the event. I know it's confusing because we're using p multiple times for like p-value, probability. P usually stands for probability or proportion, but P is true probability, and this stands for probability of the event. So the event that the bus is on time, and then the probability of said event. I mean, it is kind of like a proportion of time the bus is on time, but we're not saying like the true proportion of the event. We're just saying probability of the event is equal to this. So in this instance, P right here means probability, but in other instances, we are talking about true proportion, where in this one, this is the defect rate, which is the true proportion, which you could say is the probability of a defect. So no, it does overlap. Oh, probability to the power. Can you expand, Savannah, on it? I wouldn't try to memorize this one down here. This one, well, when you raise it to a power, you're talking about things. What rule are we incorporating right here when we're doing this? When we're raising it to a power, we're actually doing what? What rule are we actually using? So when we raise to powers, we're actually doing this. So what rule are we actually doing? So that's what we're actually doing in the background. I'm going to put it back to what it was. So we're actually doing the what? Raising to a power is actually the what rule? Raising to a power is actually the multiplication rule. And so the multiplication rule requires that things are independent, which this problem would assume. Yep, multiplication rule. Yep, raising to a power is the multiplication rule. Yep. And so, and so we're just doing multiplication rule on this to say it's not on time and not on time. So if we were to put words here, we would say and. That's very important to understand that the multiplication rule uses the word and the addition rule uses the word or right here. So knowing these sorts of patterns right here, that when you multiply, you're checking to see if things are independent. And down here, doing disjoint. So very important to know when you're adding things, you're checking if they're disjoint. And when you're multiplying, you're checking to see if they're independent. And then we have the notes there that multiplication uses and or uses disjoint right there. So very, very good stuff. What other questions are there? Any chapter 13? Anyone doing chapter 13 right now? You're welcome, Savannah. Good practice. Chapter 13? Any chapter 13 today? If you're watching Office Hours, maybe I need to send out a thing on the Discord. Say like, Office Hours going on. Need help with chapter 13. Join Office Hours. Let me send it out. Maybe it's because like the assignments are a little bit further away. Let's see here. Can we do homework? Yeah, which one? Name a problem and we can get it done. Okay. The 10% rule? So what does the 10% rule mean? What does the 10% rule mean? Like, explain to me what the 10% rule means. We have random, 10%, and then the third one depends on the type of the data we're working with. So what does the 10% rule mean? What does the 10% rule mean? What does it mean? Chapter 8, confused on a concert production company. Yeah, double down right here, Jesse. You got it. Chapter 8 quiz. Okay. I think it's an extrapolation one. Yep. You must sample less than 10% of the population. So when you sample less than 10% of the population, you have to look at your sample size and the population size and ask, is my sample size less than 10% of the population? Sometimes you have to kind of do it theoretically. And so if we say we talk to like 20 UTK students, that'd be way less than 10% of all UTK students because there's like tons and tons of UTK students. So you have to think, what is my sample size? I talked to this many. What is the size of the population? Which sometimes you have to kind of think about theoretically. Like if they say they talk to so many US citizens, well, usually there's nothing mathematically, right? Well, no, sometimes you know the answer though. Sometimes it'll give you the answer. It'll say like, there are this many in the population. So sometimes you have to theorize, sometimes you have to know it. But like if we talk to people in the US, do you think a sample of 30,000 would be less than 10% of the US population? So that's where you would do a sample of 30,000. Is that less than 10% of the US population? So then you have to be like, So you always want to mark those things and think, what is capital N? So that's capital N right there. Step 201, chapter 8 quiz. And then we got some chapter 14 right there. Cool. Okay, we'll take a little one next. Here we go. Let's go to the main screen. Okay, good to see your page. So we'll throw out some points for Paige right there. So now we got a concert production company examined its records. The manager made the following scatter plot. Okay, so they actually have two venues here for this one. So they're looking at a smaller and larger venue. Okay, so when you look at this, you would have two different lines. Line there, line there. Okay. And describe the relationship between talent cost and total revenue. The scatter plot shows a strong negative. No. Shows so it's got to be positive. There's one outlier that stands out apart from the majority of the data. Yeah, that one over there. I think that's what they're talking about. So not this one, actually. Oh, no. There we go. Both fingers are they different? Which one's larger or smaller? Red. Larger. The larger has more variability. Good. There's another one. Okay, let's find it. Concert production company. Here we go. Is it this one? So this one shows where they're on two different. Look at the heteroscedasticity scatter on that one. Is it this one here? No, it's not this one. Oh my gosh, too much. They really like concert productions here. Let's go find the concert. Here we go. Is it this one? Okay, good. I was like, is there 4 concert production ones? A concert production is looking for advanced sales to forget. They're like, man, students love concerts. Let's write a bunch of questions about this. The company scatter plot shows the advanced sales versus total revenue. So there's their revenue. There's the ooh. What do you immediately notice on this, Jesse? I don't know if you immediately notice it, but I do. What do you notice about this? I think this is the way the question's going to go. Well, there's a lot of issues with this. It does look curved. I noticed that too. So it looks curved. And then there's no data. There's no data below 15. So that's some things to note right there. A performer who refuses to permit advanced sales would like to predict their... yeah. So what would be the problem with using this model? Yeah, this does point to it then. What would be the problem with using this model to predict the revenue for a performer who doesn't use advanced sales? So what's the problem with this model right here? So don't even look at their answers. This is a matter of what? What is the problem with this model? Since there's no data, we're outside the scope of the X's. And the X only goes from like here to here. So our model only goes from here to here. So what are we doing by predicting for that performer? We're actually doing a what? Which is the point of this problem. So we're actually doing a what? And this is a key word to remember. That's why I want you to remember it before we click in the answers. We're actually doing a what? And this is something, remember, we're outside the scope of our X's. Extrapolation. So we are, and great job, Jesse, right there. The point is far from the other ones used for making the model. Used to find the model for, we're finding total revenue. Therefore, the extrapolation is not valid. It's a weird way. It should just say they're extrapolating. Okay, so they're using a model for this. Therefore, let's see what they ask. What would it be wise to assume that the model is accurately predicting? Okay, so they're asking if the model is accurate. It is extrapolation. So they want the model. I could get that last one wrong. Yeah. Therefore, the extrapolation is not valid. It's not that the model isn't. This is weird. I really don't like the way they phrase that. We obviously know it's extrapolation. Why would it be unwise to assume the model accurately predicts? Well, yeah, extrapolation right there. Well, the model could be accurate, and that's a different issue. Model accuracy is how well does the model predict the points within the scope of the X? That's why I was a little bit concerned on that, and I was thinking it might be a wrong answer. I would not phrase the question like this. The whole point of this is to show you that it's an extrapolation. Does that make sense, Jesse? Like, I don't like the exact way they phrased that at the end. Like, is the model making accurate predictions in 320? We would check that via check regression. So this is the model making accurate predictions right here. And then we actually have an extrapolation check, which we could use to check, and I need some new data to make it work, where we could see if this is an extrapolation of our model. Yeah, so the whole point of the question is literally to show you that to predict for someone who would not use advanced sales is to do an extrapolation of the model. And so that really doesn't impact the model's accuracy, but they did kind of get me with the way they worded this. Would it be unwise to assume this model accurately predicts? So it's not going to accurately predict that point. That's the issue. Or, well, I guess it's not that it doesn't accurately predict it, it's that we shouldn't use it. It's unwise to use it because extrapolation is predicting outside the bounds of the x's. Yeah, I don't like the way it's yeah, it's the whole point is predicting down here on the far side is far outside the scope of the x's. That means we're extrapolating, and it would be unwise to make a prediction that is that far away from the scope of the x's. And this is the thing that I do like students to know. The truth is you can extrapolate a little bit. You could go down here and do a little extrapolation outside the model, but you generally don't go too far, and it's way far away at that point. What is way far away? We usually make it obvious on the test. We're not going to put something right at the edge, but even then it is an extrapolation. But also, here's what's really cool is the model actually has prediction bounds that go haywire. They go crazy when you go further out. So we actually would have confidence intervals that would say like, well, we're really uncertain what would happen here. So we do have statistical ways of handling this with confidence intervals. They'd probably be even a little bit wider on the start, but we do have ways of handling that. So the mathematics is there to back us up. So we could make a prediction, but then also mention extrapolation because we don't know if the form continues. Dun, dun, dun. Sometimes I wonder, company sells salmon. Oh, I think we started that one, right? Company sells salmon. A company sells salmon. Thank you, Jesse, so much, and Savannah, and anyone else here right now. Jesse, probably everyone doing homeworks is doing the ones you're doing. They're like, oh man, he didn't do my question, but it's the ones you picked, Jesse. Thank you so much. I really appreciate it. Is it the homework? Did you say the salmon one? It is the homework. Ooh, what is? Oh, that's I clicked confidence interval. So I was like, why does that exist? I literally clicked the wrong homework, and I was like, wait, why does this say confidence intervals? And I was like, well, that's weird. Wrong homework. All right, here we go. This is a neat one. Yeah, nice. A food company sells salmon. Okay. Food company. Wow. We could just do all chapter 14 homework. Let's just do that right here. I guess maybe we could do the quiz tomorrow, and I could say we did the homework during office hours. Check out the homework. Let's do the quiz. Quiz is tougher. Yeah, no, that's appreciated and great practice. So here, let's go do it. Let's check it out. Okay, so with this chapter, we were talking about earlier that you need to know the notation. Here's all the notation down here. We have the sample mean. You're welcome, Savannah. We have the sample mean, the true standard deviation, the expected sample mean, the standard deviation for the sample mean, the sample size, and the population. Some of this, some will include all of it. The main part on this one is we need to find what is going to be the key, because it's asking us down here standard deviation y bar. So if it wants to know this is SD y bar is equal to sigma over square root of n. So we should go up top and identify sigma. What is sigma? Sigma is the true standard deviation. So what is the true standard deviation for all salmon? What is the true standard deviation for all salmon? What is the true standard deviation for all salmon? Up there, up top. Is it 4? Yours might be 4. Mine is 3, I think. So right here, there it is sigma right there. There is sigma. And so sigma is the true standard deviation. And then each of these containers has a different amount of salmon in it. So now a box has 4. A carton has 16. A pallet has 121. And we know what's really interesting about these? 4, 16, and 121 are all perfect whats. Like 4, 16, and 121 are all perfect whats. Very interesting it uses those numbers. They're all perfect whats. They're all perfect squares. So it's 2, 4, 11. So they're all perfect squares if you square root them, because that's what we're going to do right here is you're going to notice that the standard deviation of the sample mean gets smaller. This is a big concept for this chapter, that as we increase n, and we'll show it here mathematically, the sampling distribution gets tighter. So if we increase n, so n is 5, the sampling distribution looks like this. If we go to 16, it looks tighter. And that's because the standard deviation over here is getting smaller by a factor of the square root of n. So it was originally 5, but 5 divided by square root of 25. Great job, Sloan, right there. 100 points. Good to see you. 5 divided by square root of 25 is 5. Such as with 16, it's 5 divided by square root of 16, which is 4, which is 1.25. Now the mean stays the same, so that's what we're doing. So this is just the standard deviation divided by the square root of n, and it's 3 divided by 2, because we're just going to plug in their sigma, which is 3 divided by square root of 4. And that's all the work we have to do for this right here. So 3 divided by 2 is 1.5, right? I should know that off the top of my head. Good. And then now we're going up here to 16. So it's 3 divided by 4. And once again, all we're doing is taking and plugging in the new number. That's all we're doing right there. Waitress believes. Yeah, we do the waitress believes. You got it. And so now we do this one. Find the standard deviation of the mean of the pallets. I think I know this one off the top of my head. Is it this? 2 decimals. No, I don't know it off the top of my head. It's 3 divided by 11. 2.7. Oh, that's interesting. There we go. And once again, this would be because you're dividing 3 by the 121 over there. So that's got right there. Good to see your tie. And so that would be the mathematics right here. And then they're going to talk about it. The distribution of salmon weights turns out to be skewed on the high side. So this goes to the large enough n condition. The large enough n condition states that we need a large enough sample size such that the distribution will be nearly normal. And so the big condition here is that it's large enough. Depending on how skewed it is, we need larger n's. So these are the conditions right here that we've written out, or these steps. What is the shape? They said it's skewed, so we'd need a much larger n, and the largest we have is 121, I believe, so that will be the one that makes it most normal. And that is for the palette, I believe they called it. So the palette right here has the most. The palettes because regardless of the underlying distribution, the sampling distribution mean approaches normal as the sample size increases. Let's see here. The palettes because as long as the underlying, no. If it's normal, the size would not matter. So that's why at the very start right here, we put if it was normal, we wouldn't need any sort of sample size. So good stuff right here. Let's mark that question because we're going to jump around a little bit on this. That was a food company. We'll do a food company. And now let's do a waitress believes. A waitress believes. Okay. This is one of the big questions that usually people get stuck on. So what is the very first thing we need to do for this question? What is the very first thing we need to do for this question? Well, we will use the apps here coming up. What is the very first thing we need to do for this question? This is where people get stuck. They say, I have no idea how to even do notation. So what is any of the notation? What is the notation? Try to solve it out here. Take a moment. Yep. Great job, Sloan. That's the true standard deviation. What else do we have here? We're on the right track. Yep. What else? And this one, the 450 would be why'd I put sum of y? Because what is that? 450 is what? Per what? Over a weekend. 450 is the sum of y. So that's her total earnings, right? So how could we figure out her average tip that she needs to make 450? So how could we figure out y bar? Yep, there it is, because y bar would equal the sum of all the observations of y over n, which is the sample size. So, and think about this. This one's not as pretty as it sometimes is. It's 111.25. If you are waiting tables and you're going to wait on 10 tables and you want to make $200, how much do you need to make on average per table? So you're going to wait on 10 tables and you want to make $200. How much would you have to make? If you want to make $200 on 10 tables, what would you need to average tip wise? Like you'd have to average this amount per tip. Like on average, you'd have to make at least what? So you have $200 you want to make over the weekend and you're only waiting 10 tables. You'd have to average how much? $20. Does that make sense? And so that's why we're doing right here, because that's the total money she wants to make. She wants to make 450, the sum of her tips. That's the sum of the Y observations. So the average tip she would need right there. So a little tricky on the notation. We had to throw in Y right there, which is observations, the sum of her tips, and then the best 1% of weekends. But we have everything we basically need, because now what we would know right here is what would she expect on average to make? So what is her expected sample mean? Oh, Sloan's on the right track with standard deviation. What is her expected sample mean? She would expect to make how much on average? How much would she expect to make on average? People doing standard deviation, I think. How much would she expect to make on average? Yep. She'd expect her average tip to be $9.60. That's what she expects her average tip to be. And then the variation in it is the following. And this is where we go over to the apps right here, because we actually meet the conditions. It's skewed to the right. So why do we meet the conditions right here? So why can we use the applets to draw this? Remember, it's skewed to the right. So explain to me here theoretically why we meet the conditions. Why do we meet the large enough n condition right here? So our data was skewed to the right. It's skewed to the right. And why do we meet the large enough n? We meet the large enough n. Why? Good practice of large enough n right here. So it should be random tables, less than 10% of all her tables. And there's basically infinite tables you could wait on. It's not greater than 100, though. So it's only skewed, though. So it's only skewed. So it said in the question, it said the data is skewed. And so what would you have to quote if you had to write this out? It's great. What's greater than 25? You are correct. Our blank of blank is what to what? You got it. So our sample size of 40 is greater than 25, so our sample size is large enough. So we had to look at our n, which was our sample size, and see that the sample size of 40 right here, since it's skewed to the right, the first step is to check the shape. And since the shape is skewed, we need a sample size of at least 25, and 40 is greater than 25, so we're good. Like if we were to write this out right here on the bottom, we'd write 40 greater than 25, technically greater or equal. And so is our sample size large enough? Yes, it is. So that's how we check it right there. We have to first check the shape. Then we have to know the number required for the shape. Yep. And so there we go. That's how we do it. Now we're going to go over to the applet right here, which I swear I opened up. I opened it in this tab. and we're going to put in that data you just found of the mean of 9.6. And this is right here. MuBot's already posted it. He said, go here for the apps. And then we put in the standard deviation, and you can put all the decimals. Now, remember how we found out that she wants to get at least $11.25? Well, right here, and this is what I love about the applets, is you can choose your rounding on the question for how many decimals you want it rounded. And this seems pretty unlikely about 1% of the time. So we can choose this, bring it over here to the question, and 4 decimal places instantly rounded. And so we should get it correct right there. So great job. Now this one says the best 1% of weekends. So the best 1% of weekends, would that be on the right side of the curve or the left side of the curve? Because this is her average tip down here that she's getting on 40 tables. So would her best 1% of weekends be on the right side or left side? And this is kind of ironic right here. Like we can literally kind of guess the answer from this. So the right side or the left side? Because this is basically, it's pretty interesting what we got My Pearson generated for us this time. The best 1% of weekends, she'd be getting some pretty awesome tips. So this is her what on the best 1-ish%? Oh, you'd have to use the applet, or we have you draw it a lot of times or show pictures. On the test, it'd be on the right, correct. And so think about this. The value should be a little bit what to 11.25. The best 1% would be a little bit to the left of it. So I'm just going to take a guess here because I think it's so funny that we basically got it. Like 448.80. And we're kind of close. We can take one more guess before it locks us out of. Well, so those are close guesses, but let's get the right answer right now. So on the best 1% of weekends, and that's what we have to do. So we're going to go over here and go to find this, find the p-value, and let's go here to the best 1%. And this is her tip. Oh, it should have been to the right of it. Gosh. So now we're going to take this average tip, multiply it by 40, because Brian doesn't know his left from his right, and it's 21, 450.21. Like I said, the answer was very close to this, and that should do it. So does that make sense right there? Yeah, it should have been to the right. Really good question right here. Knowing this, knowing how to do these is pretty good. She wants to make $10 on 60 tables. So you just plug in, find the mean and the standard deviation. How's that looking, Jesse, Savannah, and Sloan? This is a tougher question. It requires multiple steps and really requires knowing your notation to get the mean and the standard deviation, and then also to get the average tip she needs, and then to plug in for the last part, the best 1% and timesing this by 40. Then good, nice job right there. So this value has to be times by 40 because that's her average tip on 40 tables. That's not what she made on 40 tables. That's her average tip on 40 tables. Probably do most of this homework, and then I might say we might do the quiz tomorrow. So we already did question 1. Question 2 talks about a standardized test. Okay. Standardized test. That's one of my favorite questions, the waiter waitress one. Okay. Awesome, Jesse. Yeah, check it out later. And thank you so much for being here, Jesse. A standardized test for graduate school admissions has a mean score of 146 and a standard deviation of 7, and a unimodal symmetric distribution of scores. That means it is normal. A test preparation organization teaches a small class of 4 students. Yeah, great job. Oh, well, great. Yeah, Sloan, you knew the answers to these. I was like, wow. A test prep organization teaches small classes of 4 students, and then their larger one teaches 64. Both organizations publish the mean scores. So what's going to be different about these classes, Sloan, right here? So you have a small class of 4 students, and then you have a larger class of 64. So what's going to be different about these classes? So what's going to be different? It's kind of like the last problem, because the key difference will be what between these classes? We'll think about the mean for both classes. We'd see that. But the key difference here between the classes, the mean won't change, correct? The larger class will have less variation in its mean, less variation in its sample mean. So we'll divide by the square root of n right here to get us smaller, because this will be 64 for the larger class versus 4 for the smaller class. So what would you expect the sampling distribution of the mean for each class to be? The distribution, both distributions will be approximately normal with a mean of this. So they will have the same mean right here. So both have about the same mean. There's the top equation. If either organization has a graduate class with a mean above 153, they'll take out a full page ad in the local school paper to advertise. Which organization is more likely? So it's basically asking which one has more variability in it, the smaller or the larger class? Which one has more variability in it, the smaller or the larger? So which one of these would have more variability in it? Variability is larger standard deviation. So which of these would have more variability in it? Smaller or the larger? We can calculate the variability. To calculate it, we do 7 over square root of 4 and 7 over square root of 64. And those will be the answers we're looking at. So it wants first the smaller. So 7 over square root of 4 is that. And 7 over square root of 64 is this. And is more likely the smaller one will have it because this, whoa, what happened? Standard deviation is 7. 7 divided by 2. 64. Oh my gosh. 64 is 8. I don't know my perfect squares. There we go. What is up with me today? Round to 2 decimal places. Sloan, is this it? Wait, what did I do wrong here? Okay, let's review. Brian went way too fast. Wait, a mean score of... Oh, it's doing z-scores. Ay. I just looked at the problem way too quickly. It's doing z-scores. So, sorry about that. Restarting the problem here real quick. It's doing z-scores. Okay. So, yeah, we have to use the z-scores here. So, let me actually write this out. I thought it was just asking the standard deviation. I should have read what it said. And so, here it is right here. Should have read it. I've done this problem before, but... So, the z-score is the sample mean minus the true mean over standard deviation over square root of n. So we need to do it for both classes right here. So for the first class, it's going to be the sample mean of 163 minus the true mean of 155 over, and what are the sizes? It's 9 and 36. And the original standard deviation was 8. So 8 square root 9. And then the other one is 8 square root 36. There we go. And so does this make sense here? Because we're finding z-scores. So we're just going to solve both these equations. And this boils down to knowing your notation, as we always talk about right here, where this is mu, this is sigma, this is the first sample size, and this is the second sample size. So we could put here, that is N1 right and 2 right there. 3 and 6, did I get it right? 9, yep. And we divide by 3 and 6, exactly. So it looks like the z-score here will be twice as much for that one. So that's kind of neat. That's 8 above, and then 8 divided by 3. And so it's 3? Is that really going to be... Double check my math here, Sloan. So that one's 3 as a z-score. And then this one over here is 8 divided by 6. And so 8 divided by that is 6. How did the decimals get out? Because it didn't hear 6. So 3 and 6 it should be. Let's find out. For the smaller organization, it's 3. For the larger organization, it's 6. It is more likely the smaller organization will have the success. There we go. Read it correctly this time. Both organizations advertise if the class has an average below this, they'll have to pay for everyone to retake the test. So what's really great is we know the standard deviations. I thought it could be simple round numbers. Been there, done that. Yeah, I do that all the time. Just make a mistake. And all we're doing now is plugging in 150 to see if 150 is odd right here. So we're just redoing these formulas. with the observed value, the observed sample mean being 150. And so we're just going to resolve the formulas where the observed sample mean is 150. We're asking like, how odd is that? That's what a z-score finds you, is how odd something is. And so that's 5 below. So the z-scores need to be negative here. So 8 divided by 3. And now we do negative 5 divided by that. So negative 1.88. Oh, great job, Sloan. And then negative 3.76, which is still double. This one works out this way because we're dividing by basically twice the number. So Sloan, thank you so much. And really, Sloan, 100 points. Great practice right here. And it looks like the small organization will be more at risk. They do have more variability, so it's more likely this could occur. And they are saying below, so you get a little worried right here because they're saying is 1.88 standard deviations below. So I would just put in the numbers as they are. And I think this does round to that right there. So let's check. There we go. Great job. It does say below. So that is a good question. It follows through using the z-score formula right here, where we do the observed sample mean minus the true mean over the standard deviation over square root of n. And so that's got it right there. Really good question. Really comes down to the notation at the end. They just have you finding z-scores twice for both organizations. And that's how we do it. Might grab some coffee here in a moment. Question number 3. A standardized test. Nope, didn't just do this one. No, wait, a waitress? Oh, it's another waiter-waitress question. Did they add another one? Let's see right here. Okay, 103.33. It's not 201. Chapter 14 homework. A waiter believes. Okay. A waiter believes his distribution of TIS has a model that is slightly skewed to the right with a mean of this and a standard deviation of this. There's mu and there's sigma because tips are quantitative. Explain why you can't determine the probability that a given tip will be at least $20. Oh, it's skewed to the right, and he's talking about singular tips. This is not the distribution of the mean. So the distribution is skewed. So that sounds right. Meaning it's not symmetric and does not meet the conditions for normal, so the probability values cannot be determined. That literally sounds like it right there. I mean, it just kind of says, can you estimate the probability at the next 4 parties? Oh, it's not a large enough n. So since it's skewed, we need a sample size of at least 25, and that's what they're getting at right here. So since it's skewed, 4 is not at least 25. Yeah, no worries. It's all about that practice, Sloan. And then not making errors, because 4 is not greater than or equal to 25. So that is nope. We cannot do it with a sample size of 4, which they're probably going to increase the sample size again. No, a sample size of 4 is probably not large enough for the central limit theorem, which is what we talk about, that the distribution becomes more normal and tighter, which is the 2 key things to know from the central limit theorem, more normal and tighter as n increases. So it's probably not large enough right there. And now we get into 10. Oof, yeah. Are they going to say 10 is kind of large enough? Oh, come on. Well, a sample of 10 parties may not be large enough. Okay. It is likely the sample average will approach the normal. Okay. The standard deviation of it is this. Probably. Okay, now we got to find that. Double check their work. Original standard deviation was 5.4. 10 square root 5.4. Okay, so this is meaning that an average tip is more than 3. That might be right. Okay, so this one doesn't find the new standard deviation. So this one's our best answer so far. A sample size of 10 parties is large enough. No, it's not large enough. It's probably not large enough. So they're kind of alluding to we could still kind of work the math on this a little bit. Yeah, it kind of don't like the way that took a turn at the end right there, saying, well, it's probably not large enough, but you could still kind of do the mathematics and talk about it being odd. They should have bumped it up to 25 and then said, yes, this is large enough now. Do you know, it should be graded very soon. I've been talking to the graders about that. I was talking to one of the graders this morning. So, yep, it should be graded very, very soon. About half the classes are graded. I'm so sorry about that. I've been talking to the graders about it, and I wonder if I should open it up here and see. But I believe it should be graded soon. Whoops. Well, man, have we done most of the homework now? Which of the following is not a condition to check estimating the, here we'll do 5 through 7 market. Is it just multiple choice? Oh, no, that's a tougher one. Not tough, but we got it. Which of the following is not a condition to check when estimating the mean of the population? And very clearly, we have the conditions over here. When it's categorical, it's success failure. And when it's quantitative, it's large enough n. Now, sorry about that, Sloan. It got kind of paused on the grading, and I've been contacting them and being like, hey. So it is, we check large enough n. We don't check that one. Okay, so this one I absolutely love because it seems very complicated. A study looked at the annual compensation rates. Okay. Study looked at. So this one seems super complicated till we remember our formulas and that the sample mean, the expected sample mean, is equal to the true mean. So the expected sample mean is equal to the true mean. And so if we mark our notation right here, so let's go ahead and mark the notation. And we have here mu, and we have here sigma. And, oh, then they're doing different sample sizes here. What chapter is exam 2 over? Review 2. And I'll show that here in a moment. Matthew, good question. So MuBot's putting the review notes in the chat right there. Go ahead and click that, and we'll check it out here right after this question. But that shows everything the exam is over. All the material has the links to study. You're welcome. Yeah. And so right here, the mean stays the same. So that value right there is going to be, the first value is literally that's just it right there. So all we do is plug in this, and it's asking for this for each one. And so let's just plug in this value. And that's the value for each one. Also, formula sheets. Yeah, Sloan knows it right there. Great job, Sloan. And so now the standard deviation is going to change, though, because the standard deviation formula is going to be sigma over square root of n, which means the first time we need to do it, we need to plug in this crazy large number right here and divide it by square root of 30. Now, here's where my life gets a little bit easier. 17,631,69. Okay. So this is x, and then we have n, and I believe it was 30, 50, 100, 200. X divided by square root of n. There we go. And there's all the answers. So once again, all you're doing is taking this number right here. You need to find square root of 30, and there's square root of 30. So 17,631.69 divided by square root of 30, and there's the first number right there. So once again, sometimes I use code to make my life a little bit easier because it's much, much easier. Oh, and why didn't I do this? It wants to 2 decimals, right? So let's just go here and go round this answer. This is the beauty of coding, which I sometimes like to show off. Makes life easier. Round these to 2 decimals, and then we can literally take the new standard deviations. Now, what's important to note, Sloan, about these standard deviations, as you notice me putting each one in, as we put each value of standard deviation in, as n increases, the standard deviations are doing what? As n increases, the standard deviations are doing what? So for larger, yep, smaller, exactly. Sloan knows what's going on right there. And so there's all the answers. Once again, check your work. It's easy to make decimal place errors on those. How close are the theoretical values? Well, the theoretical values are a simulation. So here's the simulated theoretical values versus the actual values, and they are actually very close. So they're reasonably close to both, and that's because a simulation will often show you what could happen. And so, yeah, a lot of work right here basically just to show that we can figure out the theoretical mean. Yeah, they're basically the same, and it's because this is a simulation, and we could simulate, like, here, I'll show you what this would look like. Someone might be like, well, what is it doing exactly? So if we were to know, like, let's say right here, the mean of a population is equal to, like, the average height of a student is equal to 70 inches tall, a male, let's say. And then the standard deviation is equal to 3. So now, if we were to go here and we were to random sample from a normal distribution, we'll just use normal, and we were to sample 10 observations where the mean is the mean, and standard deviation, there's 10 observations. So now with this, Let's go through this process and let's store this value. Let's store it as x. Let's take the mean of x, and we've now just found a y bar. So this is a singular y bar right here. And so with this being a singular, you know what I'm going to do and make my life easier and choose 9 students. Because watch this. If we were to repeat this process, this is what it would look like. We're going to go here to 4 and go for the variable I in the vector 1 through 10,000 simulations. And we're going to store into y bar. We're going to store into the first position, the first y bar, and do the simulation right here. We'll have to recreate the x, and let's run it. And now we've gone here, we've made 10,000 y bars. So here's the original histogram, or let's look what the original data looks like if we were to do a bunch of samples of it. Here's what the original data looks like. Notice the variation goes from about 60 to 85. Here is the histogram of the sample means. What do you notice is the difference between these two distributions? They're both centered at 70, but the new distribution is much tighter, and they're both normal. They're both normal, and the new distribution is much tighter because this is the distribution of sample means of what is possible. If we go here and get the mean of the sample means via the simulation, it's basically 70. And if we get the standard deviation, I chose 9 because now it's basically 1. So theoretically, I knew these should be 70 or 1. And here's a different simulation. If we just rerun it, we will get very similar values. You see now it's basically 70 and 1. So you're going to get about 70 and 1 every time you do the simulation. Did that help any, Sloan? Like, this is what they're doing with their simulation. This was 10,000 simulations of a sample size of 9. I could change it right here to larger sample sizes, and then we would see if I bring it to 100, the new standard deviation is going to be 0.3. So there's, oh wait, did I not change? Oh, and this needs to be 100 now. There we go. And now it's 0.3. Yep, and so that right there is a new simulation. Notice the new distribution is even tighter versus the original one right here is not tight at all. And so now the standard deviation is much smaller because now I'm doing the mean of 100 observations. So that's how we do it in code, and that's how they're doing it right there. Of course, you're not required to do those sorts of answers, but the mean stays the same, and the standard deviation gets smaller, and the simulation shows that, and the theoretical values, I knew it should be about 0.3 and always should be about 70. Like if I resimulate this, 70 and 0.3 are going to be the answer pretty much every time, but the simulations will come to different results. Cool. I like that question. Last question right here. Basically the same thing, the histogram to the right. We're going to do, oh, but it's skewed this time. Dun, dun, dun. The histogram to the right. Hey, Will, good to see you here. The histogram to the right shows the annual compensations in $1,000 of chief executive officers, CEOs of the 800 companies. The average compensation was $1,000. Oh, and $1,000 is this. So that's like $8.2 million. And the standard deviation is this. A research organization simulated sample means by drawing sample sizes of this with replacement. The accompanying histogram shows the distribution of means. So if you look, it is skewed. So we're going to need a larger sample size, probably about at 100. And, oh, they're showing you that it's very skewed, and even 100's not doing it. So this is a very, very skewed. So they're pulling some tricks out of their book for the last question right here. They're saying this is extremely skewed. So if you look at 30, still skewed. 50, still skewed. 100, still skewed. 200, still skewed. So I guess I'll mention this in class. You're welcome, Will. The more skewed it is, the larger n needs to be. And so I think they're getting at 200. It might not even be normal enough. Describe the histogram of total compensations. This. Well, that's skewed to the right. That's obvious. That's skewed. Explain how these histograms of the simulated sample distributions with the central limit say about the model. The simulations support what the central limit theorem says about the sampling distributions. Central limit theorem is a theorem, so simulations have to support a theorem because theorems are mathematical truths about reality. Because as the sample size increases, the peak of the histogram is where the mean is at. So the mean is going to stay at the mean. It's going to stay right there at the 8,000 or so. Right there, there's the 8,000. It's going to stays about the same. The shape of the distribution becomes more normal, and the variability of the means gets smaller. And that is literally the central limit theorem. As n increases, it becomes more normal and tighter. And you can see other examples in our slides here too, where we show, I thought we had that. Oh, it's a little later, isn't it? Where you can see the same sort of thing. As n increases, the mean is going to stay about at the same spot, and the distribution is going to become tighter and more normal as n increases. The more skewed it is, the larger n needs to be. So pretty good question right there. Oh, one more. Let's see. Comment on the rule of thumb that with a sample size of at least 30, the sample distribution of the mean is normal. So that's not a rule of thumb. 30 and it's not normal. So that's not a real rule of thumb. Since the sampling distribution of the means for the simulation, samples of any size remain skewed. Let's see here. This looks like our best answer so far. Since the distribution of the means for the sampling distribution for the sample size of each, no, it's not approximate normal, is less skewed. The rule of thumb, but the rule of thumb says with the sample size of at least 30, no. Since the sampling distribution of the means for the sampling becomes less, doesn't become less normal. So the only two answers we have right here is B and D. The rule of thumb does not hold for highly skewed. We need very, very large sample sizes. So you could have, people might be wondering, over here we put, where was it? Very skewed. We could say insanely skewed. Like skewed or very, very skewed. So if it's very, very skewed, there we go. You might need like 500. And then if it's extremely crazy skewed, you might need like 5,000. The best thing you could do is simulate it to see what's going on. But generally, the more skewed it is, the larger n needs to be. The notes mention 1, 25, 100. Once again, we generally talk about these things in a question to say that it's skewed. A lot of the questions really highlight this. But the concept of large enough n is that the more skewed it is, and this is very, 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 very skewed. Just look at the number line goes from 0 to 20,000 or so. So because of that, the sample size of 200 apparently isn't even large enough. We need an even larger n. So, but what if it's insanely skewed? Well, then you need like 5,000. So it all depends because things can always be more and more skewed. So the more skewed it is, the larger n needs to be. And it's important to understand the condition like that, why it's called large enough. You have to look at the shape of it, which is the first thing we talk about. And if it's normal, well, then you only need a sample size of 1. If it's skewed, sample size of 25. If it's very skewed, sample size of 100. And when it's very, very skewed, you could need like 500. Well, we got all of chapter 14 homework done. All chapter 14 done. What other questions are there? I'm knocking things down right here. What other questions are there? On number 4 on the exam review, circle the p-value of the slope. Yep. Yep. Let's go check it out. Number 4 exam review. Thank you, Sloan. Here we go. Put this out of order. Let's go look at that exam review. Here we go. Okay. So if you were to get something like this on the test, oh yeah. When is a p-value statistically significant, Sloan? When is a p-value statistically significant? So when is a p-value statistically significant? Below 0.05. P-values are probabilities. And what do we care about? The p-value of the intercept or the p-value of the slope? Which one of those do we care about? This is the intercept. This is the slope. We care about the p-value of the slope. So, is the linear relationship statistically significant? Yes. Circle one value that on the output that tells you this. Now, jump, when something is statistically significant in jump, it actually adds a star to it. So do you see the star right over there? So that little star right there, which I might be covering up now. That star right there means statistical significance. So think about, because I think you were saying it. So think about it, Sloan, is 0.00006 less than 0.05. Does that make sense? Is 0.00006 less than 0.05? So is that the case? So is 0.00006 less than 0.05? Yeah, no worries, no worries. That can do it sometimes. Describe what it means for a linear relationship to be statistically significant. There we go. So it's kind of a good answer right there. It means we think something's going on. It means so the relationship between x and y is unlikely by random chance, meaning that we think the line describes some variation. Regression's a big one. Like, because we did it so long ago, students look at something like this right here and they are like, wait, what in the world is this? And then it really comes down to notation. Like, this is B0, this is B1, this is X, and that's Y hat right there. This is R squared, this is N, that's the Y bar. The other things don't really matter. We did the Waitress Believes. We'll do a speed run of it right here. So we did Waitress Believes. We got it right over here. Waitress Believes right there at 45 minutes in. So we'll do a speed run version of it. And so get ready, Mackenzie. But we also have the slower version too. So I like to do things different each time if we do it twice. So you get a different version of it. We'll do the speed run version of it here. But knowing what all these values mean right here is going to be the key thing. A lot of people forget like what their values mean. What is R squared? The percent of variation Y explained by the variation X. They forget what the intercept means. It's when X is equal to 0, we expect Y to equal B0. They forget what B1 means. For each 1 unit increase in X, we expect Y to increase by B1. So those things right there. A Waitress Believes. Let's go check out that one. Here we go. 125. A Waitress Believes. Let's go check it out. Okay. So we did this one, but we actually X'd out of it. I think that's where we like changed things up. Here we go. Yeah, that's the big thing. A lot of people do that right there, Sloan, 100 points. A lot of people just use R and R squared interchangeably. So what, Sloan, once again, what's going to be the key to this problem right here? What is the key to this problem? We can look at our previous version of it right here. What is the key to this problem right here? The key to this problem will be what? The key to this problem and most problems on the remainder of the semester will be knowing your what?
Notation, brother.
Notation, brother. Okay, so we have to know the notation here. So find all the notation, Mackenzie. What notation can we find? We've got this. We got this. What notation is there? It says a waitress believes the distribution of her tips has a model that is slightly skewed to the right with a mean of this and a standard deviation of this. So what is all the notation? And then she usually waits on about 60 parties over a weekend. So we need to mark all the notation. Every bit of it. This is the key to these problems. We start off today's office hours with notation, also talking about it and making sure we know every little bit of it from each problem, like knowing what mu, y bar is, p hat, all those things right there. I think great job right there. And we even mentioned that this one's a weird one because this is the sum of their tips. That's the sum of their tips. So this is their parties, this is the standard deviation, and this is the mean. So now we need to solve some formulas down here. Mu y bar equals mu. So if they usually make $9.40 on a table, they would expect an average tip of $9.40. And that's expected sample mean. Important thing to see right there. That's like, I'd expect a sample mean of $9.40. The standard deviation is going to be sigma over square root of n, which is their original standard deviation over square root of 60. And so then we solve this out. There we go. And that's the new standard deviation. But think about this. And Sloan's already got right there. We take the sum of the y's. So Mackenzie, think about this one. If you want to make $300 and you can only wait on 10 tables, how much would you have to make on each table? You want to make $300 over the weekend, and you're only going to wait on 10 tables. So how much would you have to make on each table to make $300? So $300 is how much you want to make, and you're only going to wait on 10 tables. So you'd say, I'd need to average this amount per table, which is what we're doing down here. Sometimes when it's nice, neat numbers, it makes sense to be like, okay, I see what's going on. So if we wanted to make $300 and we only had 10 tables to wait on, we'd have to make $30 per table on average. And so we're trying to figure out the average tip right here. So this formula is equal to y bar right there. About $30 table, yep, on average. So this is the formula for y bar right here, which is what we'd have to make on average, which is the sum of all the observations. So we're summing up all our tips, and we're dividing by the total to see, like, on average, we would make this much. So that is the formula for y bar. So a little tricky because we don't really mention the sum of the observations much. But now we're going over to the apps right here. Sloan knows exactly where we're going because now it becomes plugging it in. Because we found the mean, or we know what the mean is. The mean is 9.40. 9.40. The standard deviation is no. Which no? 0.0. I have that on the calculator still. And then we need to put in the value 10.8333. And is it really exactly 5%? I think I might say to 4 decimals. There it is right there. So this is a pretty unlikely occurrence. It would only occur about 4.88% of the time right there. So pretty unlikely occurrence. We're on the far end of the curve right there. Pretty unlikely for this to occur. I should do that one. And now we want the best 10% of such weekends. So the best 10% of weekends, we need to go back here and change it back over to finding the x from the p-value. And so this is the best 10% of weekends, but this is our what on the best 10% of weekends. This is our what on the best 10% of weekends. That is our what on the best 10% of weekends. That's not the tip we get on the best 10% of weekends. That's our what on the best 10% of weekends. So that's not the tip we get. We didn't make $10.51. That's our average per table. And then we waited on 60 tables, right? So if we waited on 60 tables and made this on average, there is how much we would make on the best 10% of such weekends, because we're just taking the average tip and multiplying it by the 60 tables we waited on. So once again, that last one right here, well, it changed the problem on me, is multiplying, and that's what happened last time, because now it'll have it unmarked. So we did it, and then because we clicked back on it. But we multiply this by 60. Does that make sense, Mackenzie, right here? This is a tough problem. It definitely comes down to knowing the notation. The better you know the notation, problem becomes a lot quicker. And it really comes down to a lot of these, like, always mark your notation. Like, each problem, mark the notation, start by saying, here's my notation, here's what I know, here's how I can use it. And yeah. Well, I think I'm going to grab a little bit of lunch, and then I'll be back. I'm back watching. You're welcome, Mackenzie. We're going to end off right here. Until then, bye for now, everyone. Bye.